Well, hello, folks. Welcome to the lecture on Chapter 4, which deals with correlation and regression analysis, but really deals with the subtitle here, and that's exploring associations between variables. Okay? And so in this chapter, you're going to really look at a few ways in which we can measure and then even ultimately use the associations that exist between variables. So up to this point, you have learned how to describe distributions using either graphs like histograms, stem and leaf plots, and by using statistics like the mean, standard deviations, medians, and interquartile range. Okay, but those have been focused on distributions based around a single variable. In this chapter, we start talking about how you can actually look at the relationships between two variables in terms of the degree in which there are associations between them. To that extent, in this chapter, we're going to learn about scatter plots, which is another graph. But this graph is one that will focus on the relationship between two variables. We'll learn the correlation coefficient, which is a way of translating, if you will, what you see in a scatter plot into a number. And then we'll talk about regression analysis, which is an interesting way of actually using that association, assuming it's there. Okay, so in terms of scatter plots, here's an example of a scatter plot that looks at the median age of marriage for women and median age of marriage for men. So each of these dots would sort of basically represent some location, country, municipality, or the sort. Okay, and so we would use a scatter plot to give us a feel for the association between two numerical variables. Now, I want to underline this idea of numerical variables. You would only do a scatter plot on two variables that are numerical, right? So if either one of these were, say, categorical, right, this would not be the graph to use. And the kinds of associations that we might be looking for can take one of three forms. It can be a positive association, a negative association, or in fact, there could be no association between the variables. So let's look at what I'm talking about here. So let's look at this graph here, which is showing a case where we have the age of years of cars, right? So each of these represents cars. And on the x-axis, we have the age of the car. And then on the y-axis, we have the miles driven. Right? And what this graph shows us, right, is that older cars tend to have more miles than newer cars, right? And newer cars tend to have fewer miles than older cars, right? So you can notice that as the car is getting older, right, so is the number of miles that the car has been driven, okay? And this would be an example of something that we would call a positive trend. So the way we might interpret this is that there is a positive association between the car age and the miles that the car has driven. Okay, so that'd be an example of a positive association or a positive trend. Let's look at a negative one. Okay, so here we have data that shows the literacy rate for a given country and then the total births per woman in that country. Okay, and if we look at this data, what we see is a slant somewhat in that direction, which shows that countries with higher literacy rates tend to have fewer births per woman, right? Countries with lower literacy rates tend to have more births per woman. Okay, and so this would be an example of a negative trend or negative association. So the way we might interpret this is that there's a negative association between literacy rate and births per woman. Okay, let's look at an example of where there's really no trend. Okay, and so here we have the age of marathon runners, right, on the x-axis, and on the y-axis we have the times, right, of the marathon. Okay, and you can see it just looks like sort of a blob. So there's virtually no trend between between the speed and the age of the marathon runner. right? Therefore, knowing the age of a marathon runner does not help predict the runner's speed in any way. So in that case, we'd say there's no association between a marathon runner's age and their speed. Okay, so you can see how we can use scatter plots to get a feel for, number one, whether or not there's any relationship, and number two, whether or not that relationship is seeming to be positive, which means that as one variable is going up, the other variable is going up, and of course vice versa, going down and down, or if there's a negative trend, where as one variable is going up, the other variable actually tends to be going down. Okay, and once again, vice versa. Right? Or, like I said, in this case, there would be no example of that. But the problem is that's okay, that's great. It gives us a sense that there might be some association between variables, but it doesn't give us a feel for the real strength of those variables. So how could we get that? Well, that allows us to introduce something called the correlation coefficient. It is typically denoted in statistics as an R, right? So anytime you see a small r, you'll know that denotes the correlation coefficient. And it's basically a way of representing the strength of a trend in numbers. So, correlation coefficient is a number r that measures the strength of the linear association between two variables. Okay, it's usually somewhere between -1, which would indicate a negative trend, and +1. Okay? If the r is close to 1, then that would indicate a very strong positive. In fact, if the r is 1, it would indicate a perfect association or relationship between two variables. Of course, that would also be true if it were -1. Okay? Right? And of course, once again, if it were in fact -1, it would be a perfect negative association. If the r is close to 0, right, then it's pretty much indicative of a weak or no association. So hopefully you can see how we can look at our r's and now get a feel for the trend, right? If it's positive, it's just simply going to be a positive number. If it's negative, it's going to be a negative number. But we also have a feel for the strength, right? The closer that number is to 1, the stronger it is, and the closer that number is to 0, the weaker it is. Okay, so let's look at some examples. Okay, so here's some examples of some positive correlations. So this would be an example of a perfect correlation, right? For every dot change on our x variable, right, there would be a associated change on our y variable. Okay, and this is an example of a perfect correlation, which frankly you never see. The only reason why we're getting this is because we're really looking at the same thing. It's just height as measured in inches versus height as measured using the metric scale. Okay, this is a correlation that's less than perfect. It's pretty high, so that would indicate a very strong linear relationship between the life expectancy of men in years and the life expectancy of women in years. Okay, as we go down to something like height and weight, right, they tend to be correlated. Once again, that's a pretty high correlation. Okay, you can see, and then finally we come to something like the city government income by the amount of private income of its citizens. Okay, now notice that as the correlation seems to be getting weaker, notice what's happening with the spread of the dots. Okay, notice that as the correlation is higher, the dots form a more linear kind of line, right? And as the correlation goes down, right, those things begin to spread out somewhat. Okay. By the way, a correlation of 0.48 is still considered a pretty strong correlation, right? So all of these would probably be what we might call significant correlations, and we'll talk about that concept of significance later in the course. Let's look at some examples of negative correlations. And so here we have the percentage of smoke-free homes on the x-axis by the percentage of smokers that are in basically high school. Okay, and notice there's a negative trend. Okay, the the lower the percentage of smoke-free homes, right, the more likely there are going to be smokers in those high schools. So as the percentage of smoke-free homes goes down, so does the percentage of kids smoking in high school. Okay. If we look at literacy rate and births for women, we kind of talked about that data already. Notice that it's sort of going down. Okay. Think about this in terms of the tenure on your job and the salary that you make. Okay. I'm sorry. Yeah. So in terms of the starting year, okay, the longer you've been on the job, which is what this would reflect, right? The higher the salary is, okay? The shortest time period in which you've been on the job, the lower the salary is, okay? And this would be an example of really the same variable just being reflected on two different metrics, and only then could you get a perfectly negative correlation. Once again, notice what happens with the dots, okay? As the number, something happened there. As the number gets bigger, the tighter, right, the dots come to forming a perfect line. So let's look at an example where there's sort of weak or no correlation. Okay, in both of these cases, right, the correlation's fairly weak, or there's no correlation. You can see that the dots seem to be kind of all over the place here. All right, let's move on. And so one of the things that's important that you're introduced to in this chapter is something called the coefficient determination. Sometimes it's called the effect size. You get it simply by taking the correlation R and squaring it, but it really measures the amount of variation in the Y variable, response variable, that can be explained by the X variable. Probably a better way of thinking about it, it reflects the amount of overlap between the two variables. And so this is oftentimes an important thing to have with your correlation. In some ways, it might be a more powerful thing to interpret. And once again, you get it just by squaring the R and then translating that decimal to a percentage. All right. So there's some rules here. One that you learn very early on is that correlation is not causation. Just because things are correlated does not mean necessarily that one of those things can cause the other. Okay, so strong correlation is not evidence of a cause and effect relationship. So therefore, we shouldn't use words like causes, makes, will, because oftentimes when we are making these kind of statements, we are implying that there is causation taking place. Okay. Instead, we should probably use words like predict, intends, and things like on average. Okay, and some of this language actually applies to the analysis that we're going to learn here in a minute. Which then leads us to the topic of regression analysis. So I'm going to pause at this point, and we're going to switch over to part 2.